Hi, this is my video number 18. Right. So I'll talk on the Hilbert-Schmidt theory of integral equation. Yeah. Hilbert-Schmidt theory of integral equation. So as an introductory words, so we deal thus far as a Freedom integral equation and so on and so forth. So the part of Freedom theory which involve a integral operators generated by real symmetric kernel is referred to as the Hilbert-Schmidt theory of integral equation. Yeah, we know what is the symmetric kernel and so on. I think we have did quite a lot on that before this. Yeah. So let's see. So in this, basically, this part is basically a little bit theoretical, but it's not that many. It's not that much. All right. We just go through. Then I give a couple of definition and a couple of very basic properties that's involved in here. Okay. So first, let's see some of the definition. All right. So first definition is on what is L2 function and L2 kernel. Yeah, L2 function and L2 kernel. So a function is said square integrable. Yeah, function is said square integrable, or let's say L2 function. So L2 function is a square integrable function. Square integrable function. If it is measurable in the finite interval, if it is measurable in the interval AB, and also it satisfies the integral a to b fx squared dx less than infinity. So if we say L2 functions, if we say L2 function, then that function is a measurable function and satisfy that integral. Okay, so we integrate from absolute of fx squared dx. It is gives some numbers, right? And the integral here, in this case, we call it, we take it as in the sense of Lebesgue. Yeah? Means it's a wider range of integral as compared to a Riemann integral. So we call this condition as a regularity condition. Yeah, regularity condition. Then on the kernel K2, this is for function L2. Now for L2 kernel, so it's almost identical to the L2 function. Yeah. So we say a kernel K, we say a kernel K is said to be L2 function or L2 kernel if we have the following. We have the following condition. Satisfy L2 kernel satisfies first that integrate a to b k xt, we need absolute there, squared dx dy, this is finite, yeah, for all xt in AB. Okay, and condition number 2, we have integrate a to b kxt squared dt, this is also finite, for all x in AB. Yeah, for all x in AB. Then condition number 3, integrate a to b kxt squared dt, this is finite, for all this one x, this one t, for all t in AB. So this is the L2 function and L2 kernel, or we also say the regularity condition. Yeah, this for function f, this is the regularity condition for f, and this is the regularity condition for the kernel. Right. Next, we look at the inner product or the scalar product of two functions. Definition: the inner product, or also known as scalar product of two functions fg. So we denote as fg, and this is defined as we integrate from a to b fx gx bar dx. Yeah, where bar denote the conjugate. Yeah, where gx bar is the conjugate for gx. Yeah, of course, in this case, if g is a real number, a real function, so which means g bar is just equal to g. Yeah, for the case of g real. Then next we look at the orthogonal function. Another definition. We say two functions are orthogonal. Two functions fx and gx are orthogonal on interval AB if we take the inner product f and q that give us 0, which is that fx gx bar dx, this is equal to 0. Yeah, so any two function satisfy that condition, we call it as we call that function orthogonal. And if you have a weak function, we say two function f and g, are orthogonal with respect to weak function, let's say omega of x, if it satisfy integrate a to b, we have omega x fx gx bar dx equal to 0. So this, when the case we have a wave function, here this is a specific case where when the wave function is equal to 1, so we have this that equal to 0. So this we call it as a f and g, we call it as a orthogonal, yeah, f and g orthogonal. And then definition of norm, or norm of a function. Definition. So norm of a function, norm of a function fx, so normally we denote as fx, yeah, fx with two line there. This is equal to integrate a to b fx bar dx to the half. Yeah, so this is also same as integrate a to b fx squared dx to the half. So if you recognize this, this is actually the inner product of function by itself. So basically this is f. So the inner product of the function with itself. So this give us that give us f. Okay. Okay. Now we look at the how can we normalize a function. So we have function. Normalize means if we take the norm of that function, it gives us 1, unity. So that's, we call it as a we call that function normalized. Okay, definition. A function fx yeah, is said to be normalized, is said to be normalized if norm of that function is equal to 1. So which means if we have non-null function, yeah, non-null function whose norm is not 0, so we can always normalize that function by its norm. Okay, we can always normalize that function with its norm. So for any function, for any non-null, which is different than 0, whose norm is not 0, norm is not 0, so we can always normalize. So we can always normalize that function. We can always normalize that function by dividing by dividing with its norm. If you can do that, then we can find the or we can say that the function is normalized. And for the autonomous system, so we have orthogonal, we have normal and normalized. Now we look at the autonomous system. So what is the autonomous system? We say a finite set of fx, a finite set, a finite or infinite set fx I that which is defined on the AB. So we say this is we say this orthogonal. Okay, we say this orthogonal. So it said this function defined on AB ax AB is said to be orthogonal if the inner product of fi fj 0, yeah, for I different than j. So for the orthonormal, yeah, so the function or the set fix is said to be orthonormal if it satisfies these two conditions. So basically we have fi fj itself are orthogonal, and number two is that fi is equal to 1 for all fi, for all I basically, yeah, for all I. So in other words, I can say the orthogonal, in other words, yeah, I can say those functions orthogonal if the inner product fi fj, yeah, this is equal to, this is 0 for I different than j, and give you 1 if I equal to j. So we call this as a orthonormal, the set we call it as a orthonormal. Okay, so an autonomous system is said to be complete. Yeah, the autonomous system means satisfy that condition. Okay, it's said to be complete if it is not proper subset of a more comprehensive autonomous system. Yeah, the system is complete if only if every L2 function orthogonal to every member of a null function. Yeah. For if this condition is satisfied, it is clear that the set cannot have a proper autonomous extension, and if there exists L2 function fx orthogonal to every member of that set and such that the norm is different than 0, then add function fj to S give a proper autonomous extension. So just notes for that. Next we look at the Hilbert space. Look at the Hilbert space, a complex Hilbert space. Yeah. Complex Hilbert space. So the complex Hilbert space, let H be a Banach space. Let H be a Banach space. There is a definition for the Banach space. You can find out those things. Be a complex Banach space. Banach space. Then H is called Hilbert space. Is called a Hilbert space. Hilbert space. If a complex number, xy, called the inner product of xy. Yeah, if the inner product of xy satisfy this three condition. Yeah. First, if the complex number xy, which is the inner product of two numbers xy, satisfies first we have the conjugate of xy, this is equal to yx. 2, we have x, this is x squared, and number 3, alpha x plus beta y, z, yeah, the inner product of beta x plus alpha x plus beta y with z, this is equal to, we have alpha xz plus beta yz. So if the inner product, yeah, if you consider a set, any set H, for example, and we take any member of those set xy, then the inner product of those set xy satisfy those three conditions, then we call that set as a Hilbert space. Okay, so let's see example. Yeah, example. We consider a Banach space consisting of n tuple of complex number. Yeah, so consider, let's say we have x with x1, x2, xn, all right, and the norm is defined as x. This is summation of xi squared to the half for I from 1 to n. So this is a Banach space. So we want to show that this kind of set is a Banach space. So show that this set is Hilbert space is a Hilbert space. Yeah, you want to show that this set is a Hilbert space. Now let's show this, or let's prove this. In order to prove this, we need to prove that the inner product satisfies those three conditions here. Okay, so for the first condition, or let's say our x is given as x1, x2, xn, yeah, and y is given as y1, yn, and z with z1, zn, and each of these x, y, and z satisfy that condition. Yeah? The norm of xy is given by that. So which means with norm of x is given that xi squared to the half I from 1 to n, and norm for y sum I1 to n yi squared to the half, and norm of z sum I to n zi squared to the half. So we need to to prove the first condition that we need to prove is that x y conjugate this is equal to yx. So we need to show that property. So let's do it. So for first property, we want to show x, y, the inner product of x conjugate, y conjugate. So this is equal to, we have, by definition of dot product, we have xi, yi, bar, alright, and conjugate everything. Conjugate everything, because the conjugate there, here bar from the definition of inner product. Okay, so what we have from there, this is just equal to, well, if you split or open up the, or expand this expression, so you might have something like x1 y1 bar plus x2 y2 bar, extend the thing, expand those things up to xn yn bar. Alright, and we have bar everything there. And the properties of the conjugate, we have, this is just equal to, for that we have x1 y1 bar and bar plus x2 y2 bar and bar plus so on, x yn bar. Okay, and that give you we have x1 bar y1 plus x2 bar y2 plus xn bar yn. Then of course you can rearrange this thing. That give you y1 x1 bar plus y2 x2 bar and so on, yn xn bar, and this give us yx. Okay, so and the property number 2, we need to show that x, the inner product of itself, is given as norm of that s squared. So by definition, again by using definition of inner product, that gives us I 1 to n, we have xi bar, this is equal to sum of I from 1 to n x squared, xi squared, and this is actually norm of x squared. So the inner product of itself is norm squared. So that satisfies the second condition. The third condition, so we need to show that alpha x plus beta y, inner product with z, we can split that one by one. So again, if we